Well, let's finish up this lecture with an example problem. This is about the only time I would suggest using ideal gas law for water is when the problem explicitly tells you to. Otherwise, it's probably not a good idea. And if it's even if it tells you to use it for a refrigerant, I wouldn't. But at any rate, it's just a terrible idea with a refrigerant, and it's not a good idea normally with water. Just because we have, number one, we have better tools, and number two, we will often deal with situations where they are approaching the phase change. But this problem asks for it, so let's give it a try, shall we? Okay, so let me switch cameras here. This problem wants us to they've given us some information here, and they want us to, given the fact that we have water, the fact we have a pressure of 3.5 megapascals, and we have a temperature of 450 degrees C. They want us to find the specific volume. And this problem is going to ask us to find the specific volume three different ways. Part A is using ideal gas law. Part B is using the generalized compressibility factor. We're going to call it Z. And part C, it's going to ask for us to use what it calls the steam tables. Those are the superheated water vapor tables. Okay. So it wants us to find the specific volume given this pressure and temperature combination. Part A is using the ideal gas. So using ideal gas law, well, where do we start? We're looking for V, and they want me to use the ideal gas law, so we're going to start there. That is P little v is equal to RT. And so that means V is equal to RT divided by P. Okay. How many equations I have? I've got one equation here. How many unknowns? Well, I know both temperature and pressure. I don't know the R value. So one equation, two unknowns. I need to find another unknown. Okay, well, what tools do we have? I'm looking for V, so what tools do I have to find R? R now becomes the unknown I'm after. Well, R is a property of the substance. That's what we call the gas constant. In this case, our substance is water. So I can go create a block over here and say, let's go look at properties. And we go to table A1 in our textbook. These are metric units. Table A1 gives us common properties of um, molar mass and gas constant and critical point properties of several substances. Okay, now water's down here at the very bottom. I can't quite get this on here, but I tell you what I can do. Let's do this. Let's see if I still have it, if I didn't close this tab earlier. Yes, perfect. So I've got the property tables on PDF from the 6th edition. Let's zoom back just a bit. So we're in metric units. If I go all the way up here to table A1, we can do that. How's that? So again, this is Shingle and Bowles, and you can see they've provided the source where they're getting these actually from American Society of Heat and Refrigerant, Air Conditioning Engineers, ASHRAE. So gas constant, units of kilojoules per kilogram. Down here, water, gas constant for water, R is 0.4615 kilojoules per kilogram Kelvin. Okay. All right. So let's go back to the camera then. Oh. And that should be all I need, right? Now it's just calculator and units. Okay, calculator and units tells me, all right, so if I say V then is equal to my R value there is 0.4615 kilojoules per kilogram Kelvin, multiplied by my temperature. And here's where I would ask the class, okay, what's my temperature? What's my temperature? And somebody will inevitably say, oh, it's 450. I say, okay, so what's my temperature? What is my temperature? 450 is not my temperature, at least not as far as the ideal gas law is concerned. My temperature is actually 723 kelvins, 723 kelvins. Or I guess I think you can multiply by 1.8 and get Rankins, right? So about 1300 Rankins. But we're not going to use that. We're going to use 723 kelvins. I can use Rankins. I cannot use Celsius. I can use kelvins. I cannot use Celsius. So my temperature here is 723 kelvins. I divide by my pressure, and I do need to make sure it's an absolute pressure. I see no reason to think this is anything but an absolute pressure, even at that, especially at that high of a pressure. Excuse me. So 3.5 megapascals. Okay. Now we could just run these numbers here, right? This is 723 times 0.4615 divided by 3.5, and I get a value here of numerically, I get 95.33 would be sufficient. And what units is it? Well, now the rookie mistake is just say, oh, it's just meters cubed per kilogram, right? No, it's not. No, it's not. What I have there is the kelvins go away. What I've got is kilojoules per kilogram per megapascal. Those are the units I have there. That is technically correct. Although with me, you're not going to get full credit because that's not a unit of specific volume. My wife is messengering me. I should probably turn that off. So, okay, what units do we need? Well, what you will find is in the metric system, if you'll often, I think we've mentioned this before, if you'll break these units down into their base, right? If I take a joule, of course, is a Newton meter, which is a kilogram meter per second squared times another meter, that is a kilogram meter squared per second squared. You don't have to memorize any of this. Just remember a joule is energy, so that's force times distance. That's a Newton meter. Force is mass times acceleration. That's a kilogram meter per second squared. Still times the meter and so on. And you can do the same thing with the Pascal. A Pascal measures pressure. That is force per unit area. So that is a Newton per meter squared. And again, a Newton is a kilogram meter per second squared per meter squared. So complex fraction says that the numerator of the denominator is actually also the denominator. So this is a kilogram per second squared per meter. That's what we end up with there. Notice that if I had a joule per Pascal, if I've got a joule per Pascal, that is a kilogram meter squared per second squared divided by a kilogram per second squared meter. And complex fraction says, well, that's the same as a kilogram meter squared per second squared times, if I flip this over, that's second squared per kilogram meter. Nope, meter goes on the top. I looked at that. I was like, that's not right. Meter goes on the top. Kilogram goes on the bottom. Yeah. So what that tells me is a joule per Pascal becomes the second squared goes away, the kilo, and yes, that's okay. The kilograms on this one goes away. I'm just left with meters cubed. The joule per Pascal is just meters cubed. Okay, Steve, how the heck does that help us? Well, remember up here, I've got a kilojoule per megapascal, not joule per Pascal. I've got a kilojoule per megapascal. So what you've actually got up there, your specific volume is equal to 95.33 kilojoules per kilogram, and then also per 1,000 kilopascals. Right, that's what I've got right here. I've got megapascals on the bottom and 1,000 kilopascals is a megapascal. So this becomes specific volume is 0.9, I'm sorry, 0.09533. Um, and then notice here I've got joules over kilopascals. That's just going to break simply down to meters cubed because it's going to be kilonewtons over kilonewtons. So it's really going to break down. The factor of 1,000 is going to go away. It's on both top and bottom. So that is going to leave me with meters cubed per kilogram. So one might say, "Hey, Steve, it's the metric system? Doesn't just everything just work out?" Well, that's the rookie mistake, is to assume it's just going to work out. It doesn't. But if you break everything down to the same magnitude, if I put kilos over kilos or joule base unit joule over Pascal, notice joule over Pascal does break down to simply a meters cubed. So part A, answer. Find the specific volume using ideal gas law. Okay. Now, part B says do it again, but use the generalized, and it won't say the Z value. It'll say use the generalized compressibility factor. Okay. So if I use the generalized compressibility factor, that means P little v is equal to ZRT. Well, I already know the R value for water. That's known. I need to know Z. Well, Z is a function of what we call the reduced pressure and the reduced temperature. We use a chart, a graph to find that. We already kind of saw that a little bit ago. Well, how do we find reduced pressure and reduced temperature? Well, we find these based off of our given pressure divided by the critical point pressure and our temperature divided by the critical point temperature. Where do we find these? Well, go look for properties, and we find those the same place that we found the R value. Scroll up. These are the critical point properties, table A1. And so water's critical temperature is 647.1. Those are kelvins. And the critical pressure is right here, 22.06. 22.06, and those units are megapascal. Okay. So notice now I can find my reduced temperature. My temperature is 723 kelvins divided by 647.1 kelvins. I can find my reduced pressure. I've got a pressure of 3.5 megapascals, and the critical point pressure for water is 22.06 megapascals. That's 220 atmospheres because zero point 0.1 kilopascals, give or take, is an atmosphere. So we can actually compute those and we use those then to go find a Z value, which I've got now in my PowerPoint slides. Let's go look at that. Okay, so let's go, we can exit this. Let's go switch over here and so we've already done part A. Yes, part A, so far so good. Okay, so let's go look at part B. We found, so we found these, right? Found these, so far so good. We can actually compute those then. I'll switch to me now. So we've got values. How do we find Z? Well, we go to this chart. And okay, so what do we got there? We've got 0.16 roughly is our reduced pressure. 1.12 is our reduced temperature. So notice that, yeah, so I've actually got it on here, but yeah, so notice that, do it in blue because of, right, basically somewhere in between here is our reduced pressure. Right? Now we could actually take a um, a ruler and get pretty close, right? So notice I didn't nail it. I got close, but I didn't quite get there. Okay. So you could put your reduced pressure in there. We got a reduced pressure of 0.16. Now our reduced temperature is 1.12. So I've got a reduced temperature here of 1.1. I've got a reduced temperature of 1.2. I can't have a line for every single one. I can't have a 1.11, 1.12, 1.13. It would just be a solid mass. So you wouldn't be able to see between anything. So I've got a curve there for 1.1, and I've got a curve for 1.2, and I've got a value of 1.12. So in between them, you can see there. And you can see what happens. They kind of all merge together. And I mean, off this diagram, I might call it 0.95, to be honest with you. And that's about the best I'm going to do. All right, about 0.95 and call it good. If you've got a fancy computer model, the text, like the textbook solutions manual does, they're going to spit out an exact value of 0.961. I don't think I would, from here, I wouldn't get 0.96. Okay. Now you can go to this diagram. Again, remember, I said that there's this guy that goes from 0 to 0.1. So it's zoomed in, it's kind of blown up. It's not as easy to read, but it's blown up. But you can see you've got a line right here for 0.16, right? We're at like 0.159, so you could actually get pretty close to that. And then notice you've got a line here for 1.1 and 1.15. This guy here and this guy here. So you can basically say, all right, well, in between those should be 1.12. And you can see what happens. You get up in here and everything just kind of merges together. And basically what it's saying is everything's converging to approximately ideal at a very, very low pressure. Everything and very close to the critical point temperature at 1.1, or especially if you go above the critical point temperature at a very low pressure, everything approaches a Z value of 1, which is an ideal gas. So anyway, you can see where those all kind of converge and intersect, and you could probably get 0.96 off of this diagram here, right? This is 1, 2, 3, 4, 5, 6. You could see it. I mean, if I would call it 0.9. I would go off of this diagram. If it's me, I'm going to go off this diagram and I'm going to call it 0.95 and call it good. And I would grade that just fine, by the way. You could go here and you could get 0.96. You could download programs off the internet, run some Python script, and you could find Python script that would mimic these curves and describe them mathematically. and you could probably get to the 0.961, and you're not going to be able to do that on a test. I'm not going to ask you to do a z-value on a test. You can. It's not hard from this diagram to do a z-value, honestly. Um, but I'm not going to ask you to. I'm going to ask you to do it one time in a homework problem, and that's fine for my class and my purposes. So, okay, what does this mean for us? Well, that means now we need to solve for a z-value. Okay, now we've got, I'm sorry, now we need to solve for a specific volume value. That's what the problem asked for originally, was find the specific volume using a z-value. Well, now I've got a z-value of 0.96. We plug that in. For me, for my purposes, I'm going to get 0.96. I'm not going to get to 0.961. I'm not going to get that third significant figure off of those charts that we have. I mean, at best, I'm probably going to get 0.95 off the first one, but you could get 0.96 off that second one, right? So you could get a second significant figure. So I'm going to round my answer to two significant figures here because that's all the precision I've got. And notice what they've done with the units here. They've broken everything down to base units, or at least to newtons. So the units cancel out this way, and that's fine. It's you know, perfectly appropriate way to do it. So you get a value over here of 0.92 if we run that out. Okay, and then the last one is using steam tables. Anytime it says you see the word steam tables, they're asking to use superheated water vapor tables, is really all they're telling you there. So using the superheated water vapor tables at a pressure of 3.5 megapascal and a temperature of 450 degrees C, we go look that up. I guess I've got it pulled up right here. Oh, I don't know why I stopped sharing. I switched the wrong screen. Yes, keep please. We can go quickly here. You want to get really, you're seeing, you want to get really quick at this. This is superheated water. We can start here and work our way back. We don't know the phase for sure, but at that temperature, it's probably superheated. There we go. This is our row for 450 degrees. This is our block for 3.5 megapascals. This is our specific volume right here, 0.9198. So again, you want to get really quick and really good at being able to find those values. Okay, that is your best value. That is your absolute best value. All the others are just estimates. Okay. So what does that mean? If at all possible, avoid using ideal gas law for water and never use it for refrigerants. If you're in my class, never use ideal gas law for refrigerant. That's a good way to tell me you're using Chegg or AI or something else or somebody that really doesn't know what they're doing. Never use ideal gas law for refrigerants. I'm not ever going to ask you to. Okay. If you do, I'm going to look at it very, very cautiously. I'm also going to look at you very cautiously if you use ideal gas law for water, unless you've explicitly been told to. This problem's okay because they've told you to. I mean, for air, for nitrogen, carbon dioxide, oxygen, things that are in a gaseous state, when we encounter them out in the wild, ideal gas law is just fine for those. Just fine for those. So. But in this case, notice for water, ideal gas law got us in the ballpark. I mean, it's one significant figure correct, right? So it's in what we call an order of magnitude. It's in the ballpark. A good Z value, if you're careful about pulling a really good Z value, you're for sure going to get one better significant figure. You can push two, maybe three significant figures with a Z value. And so notice that to two significant figures, we now agree with the actual value. Those table properties are as close to an actual correct value as you're going to get for water in R134. Hence the reason I'm saying don't use ideal gas law for a water in R134, because by the time you've established you have a gaseous quantity, you're already to where you need to be to just use the tables anyway. Okay. Questions, comments, complaints, leave them for me in the comments, send me an email, and that's what I got. So. All right, guys, we'll pick up chapter 4 for there with my class and my students. I'll do a review video for it because we've got exam one coming up after this point. So, but then, like I said, the next lecture after this, we'll start looking at chapter four. See you guys.